Welcome to Building Cisco Multi-Layer Switched Networks, BCMSN Lab Number 1. In BCMSN Lab Number 1, we're going to perform some fundamental operations on Catalyst switches. Specifically in this lab, we have a couple of Catalyst 3550s, and they are interconnected via two connections. And the very first thing we're going to do is to create an ether channel where we're logically bonding together those connections. And we will also verify that ether channel configuration. And with that ether channel configuration in place, we're going to create a trunk across that ether channel. A trunk can carry traffic for more than one VLAN. And instead of having to go to each switch and create new VLANs on each switch, we are going to leverage VTP, the VLAN trunk protocol. It's not called a trunk protocol because it acts as a trunking protocol, but it's a protocol that runs over a trunk. We will designate both of our switches as VTP servers, and when we create VLANs on one VTP server, those VLANs will be propagated across the trunk, which is routing on the ether channel to the other VTP server, and those VLANs will appear on that other switch. Then we're going to add a couple of VLANs and verify the VLANs created on one switch are indeed propagated and learned by the other switch. And as a final step, we're going to assign different switch ports to the VLANs that we created. But let's begin by taking a look at the topology on screen. Notice we have a couple of switches, DSW1 and DSW2. They are interconnected with two connections. What we want to do in the first portion of this lab is to go to each of those switches and configure them to support ether channel. We're going to configure them so that they will send PAG-P frames, port aggregation protocol frames, which will support the creation of an ether channel where we can have multiple physical links logically bonded together into this virtual interface. Let's take a look at the syntax we're going to use to accomplish that. In global configuration mode, we're going to say interface range, and we can specify a range of interfaces. We say what the interface type is, such as Gigabit Ethernet or Fast Ethernet. We give the starting slot/port identifier. We give a space, and that's critical. We give a hyphen and then another space followed by the ending port on that slot. For example, we could say something like interface space range space gig space 0/9 space hyphen space 10. That takes us into interface range configuration mode. It's from here that we can create our ether channel and say that all of the interfaces in this range belong to this logical ether channel. We can do that with the channel-group command. We say channel-group, give a number of that channel group, and say what the mode is. In our lab, we're going to set the modes on each switch to desirable. They're going to be sending PAG-P frames in an attempt to create an ether channel. Let's now go configure this ether channel on our switches, DSW1 and DSW2. Let's begin our configuration on switch DSW1, distribution layer switch number 1. We go into global configuration mode and say that we want to configure not a single interface but a range of interfaces. We can do that with the command interface range, and we specify the interface type. In this case, it's a gigabit interface. And we're going to begin with interface gigabit 0/9, give a space, and give a hyphen, and give another space. And by the way, those spaces are critical. This command will not work without those spaces on each side of the hyphen. And we're going to end on interface gigabit 0/10. This takes us into interface range configuration mode. From here, we can specify that we wish to create an ether channel. We do that with the channel group command. We say channel-group, let's give a number of 1, and we say that the mode is desirable. Desirable says that we are actively going to be sending PAG-P frames, port aggregation protocol frames, to the other side of these links in an attempt to form an ether channel. An ether channel will logically bond these physical connections into a logical connection. And we have to go do this on the other side as well because we're getting some feedback on the screen that says PAG-P, it is not enabled on the remote port. let's go over to switch DSW2, and the way we're going to access that switch is via an access server. Notice that the prompt changes to AS1. That's the access server that I'm using to connect to these two distribution layer switches. Let's resume a session I have already going with switch DSW2, and once again go into global configuration mode, specify that we want to configure a range of interfaces. We say interface range gigabit 0/9 space hyphen space 10. In interface range configuration mode, we once again configure our channel group numbered 1 with a mode of desirable. We are going to be actively sending PAG-P frames. And we're getting some feedback on the screen right now indicating that this Ether channel is up. We have created a virtual interface called Port Channel 1. Port Channel 1 is our virtual Ether channel interface. Let's verify that this Ether channel is indeed up and functioning with the command show Ether channel summary. This command tells us that we have gigabit 0/9 and gigabit 0/10 participating in this Ether channel. Now that the Ether channel is up, our next step is to configure a trunk across this Ether channel connection. Let's talk about how to do that. Now that we have an Ether channel created, the next thing we want to do is to create a trunk across that Ether channel. And a trunk is a connection that is able to carry traffic for more than one VLAN. And therefore, since we're going to be carrying traffic potentially for multiple VLANs, an Ether channel is oftentimes a great choice for a place to create a trunk, because an Ether channel gives us extra bandwidth to accommodate the traffic from all of those different VLANs. And there are different ways of creating a trunk. Much like the PAG-P frames, the port aggregation protocol frames that Ether channel used to set up an Ether channel, trunking can use DTP, the dynamic trunking protocol, in order to set up a trunk. We have one switch set to desirable mode, and that switch can send DTP frames to the other side, and maybe that other switch is set to auto mode. In other words, if that other switch receives DTP frames, it can negotiate the creation of a trunk. In our lab, however, we're going to force each of these switches to be operating in trunk mode. And specifically, we want to create an IEEE 802.1Q trunk, as opposed to something like Cisco's proprietary ISL trunk. Here's the syntax that's going to allow us to do that. In interface configuration mode, we're going to specify the encapsulation type. We're going to say switch port trunk encapsulation .1Q. But to be technically accurate, please realize that .1Q is not actually encapsulating the original frame. .1Q is adding 4 bytes, 4 tag bytes, to the end of that frame. So it's not technically encapsulation, but we are using this command to specify the trunking format that we want to use. Once we have specified .1Q, then we're going to say that we want this switch to be operating in trunk mode. We're forcing the interfaces to operate in trunk mode in this lab instead of dynamically forming a trunk. Let's go back out now and configure this trunk on our switches. On switch DSW2, let's go into interface configuration mode, not for a physical interface, but for the port-channel 1 interface. This is the virtual interface that was created when we set up our Ether channel. From here, let's say that we want to use the .1Q trunk encapsulation type. We say switch port trunk encapsulation .1Q, and I also want to force this port into acting as a trunk port. So we can say switch port mode trunk. Now let's move back over to switch DSW1 and give a mirrored configuration. We go into interface port channel 1. We say that we want to use the .1Q trunking encapsulation. And we also indicate that we want to force this port into acting as a trunk port. We do that with the command switch port mode trunk. At this point, we have built a trunk across our ether channel that we created in the previous step. Let's verify that we do have a trunk set up. We can use the command show interfaces trunk, and we see that yes, indeed, we do have a trunk configured. The next thing we might want to do is to configure VTP, the VLAN trunk protocol. Let's talk a bit more about that. Now that we have created an ether channel and we have formed a .1Q trunk across that ether channel, we are able to carry traffic for multiple VLANs. And a VLAN can be thought of as a broadcast domain. Oftentimes we think of a VLAN as acting much like a subnet. And notice on screen that in this lab we would like to have a couple of VLANs. One VLAN for the lobby, which would include the lobby PC attached to DSW1 and the lobby server attached to DSW2. We then want to have a second VLAN for the employees. We have an employee PC and an employee server. And one option for doing this is to go to each switch and create those two VLANs. However, that solution of creating a VLAN on each switch, it might not scale very well in very large environments. Fortunately, Cisco gives us a tool called VTP, the VLAN Trunk Protocol. What we can do is create a VLAN on one switch, and the VTP protocol can propagate that information to neighboring switches. And we can configure our switch to operate in different VTP modes. In our lab, we're going to set up each switch to operate as a VTP server. A VTP server, and as we're going to demonstrate, we can have more than one VTP server in a network, but a VTP server allows us to create a VLAN, delete a VLAN, and learn new information via VTP advertisements that are sent to us by neighboring switches. We could also put a switch in VTP client mode, and on that switch we would not be able to add or delete a VLAN, but we could learn about VLAN changes through those VTP advertisements. Or alternately, we could configure our switch to operate in VTP transparent mode. In transparent mode, on that local switch, we can add VLANs, delete VLANs, but we are not going to update our local VLAN database based on VTP advertisements that we receive. We can simply transparently forward those VTP advertisements through our switch without updating our VLAN database. But again, in our lab, we're going to set both switches to VTP server mode. Then on switch DSW2, we're going to create a couple of VLANs, one for the lobby and one for the employees. After we do this, a VTP advertisement is going to be sent from DSW2 over to DSW1, and at that time, DSW1 will dynamically learn about those new VLANs. Then, once the switches know about the existence of these different VLANs, we're going to conclude this lab by assigning switch ports to those VLANs. For example, on DSW1, we want port gigabit 0/4 to belong to the lobby VLAN, which we will number VLAN 10. And we want gigabit 0/5 to belong to the employee VLAN, which we will number VLAN 20. Let's see the syntax we'll use to set this up. In global configuration mode for our switch, we're going to say VTP mode server in our lab. However, realize we could have a mixture of VTP servers, clients, and transparent mode VTP switches. We're also going to create a VTP domain name, and in order to accept an advertisement coming from a neighboring switch, the VTP domain names have to match. We will call our VTP domain name bcmsn. And to prevent a rogue switch from being added to the network with the same VTP domain name and possibly corrupting our VLAN database by sending us an invalid VTP advertisement, we're going to protect our VLAN database by setting up a VTP password. We will use a VTP password of Cisco Press. Then, after VTP is configured, we are going to add a couple of VLANs. We can add a VLAN on a switch that is configured as a VTP server or as a transparent mode VTP switch. We could not do this on a VTP client, but we're going to be using VTP servers. We're going to say VLAN and give a number. We will say VLAN 10, And we will also say VLAN 20 to create those two different VLANs. After we say VLAN and give a number, this takes us into VLAN configuration mode. And as a best practice in VLAN configuration mode, I like to name the VLAN. That way, as we're doing our verification and issuing the show VLAN command, instead of just saying a number for a VLAN, we see a descriptive name. It helps us better visualize the network. And as a final step, we will want to assign switch ports to these different VLANs. We will do that with the command switchport access VLAN followed by the VLAN number. Let's go back out to our switches now and set this up. As we begin to set up VTP, let's go into global configuration mode for DSW1 and say that we want the VTP mode for this switch to be a server. In other words, we want to be able to create and delete VLANs from this switch. Let's also set the VTP domain name to bcmsn, and that's going to have to match among other switches that are also members of this domain. We can also, as a best practice, set a VTP password. This is not required, but I like to do it as a best practice. Let's say that the password is Cisco Press. That way we cannot have a rogue switch added to the network and override our database because it would not have the appropriate password. Now that we've set up VTP on this switch, let's go over to DSW2 and give a mirrored configuration. Again, we're going to say that the VTP mode is going to be a server, although we could have it be a client. We are going to say that the VTP domain name is going to be bcmsn, and the VTP password is going to be, once again, Cisco Press. Now let's test this out. Let's create a couple of VLANs and see if they are successfully propagated across the trunk that we have formed on our Ether channel. To do that, let's get back into global configuration mode and say VLAN 10. And for VLAN 10, if you recall from our topology, VLAN 10 is going to be used for the lobby. So let's give this VLAN a name. Let's call it the lobby VLAN. Let's create another VLAN, VLAN 20. Let's give it a name of employee VLAN. We can verify that these VLANs were created on this switch by saying show VLAN. We see that yes, indeed they were. We have the lobby VLAN, VLAN 10, the employee VLAN, VLAN 20. But the question now is, were these VLANs successfully propagated across the trunk that's riding on our Ether channel? Did switch DSW1 learn about these newly created VLANs? Let's go check. Let's go over to DSW1 and let's do a show VLAN. And look at this. We do indeed have the lobby VLAN and the employee VLAN created on switch DSW1. That was propagated automatically thanks to VTP, the VLAN trunk protocol. And as a final step in this lab, now that both switches know about these VLANs, let's assign some ports to these VLANs. Let's go into interface gigabit 0/4, and let's say that this is a member of VLAN 10. In other words, we may be plugging that lobby PC into interface gigabit 0/4. We can say switch port access VLAN 10. Next, let's go into interface gigabit 0/5 and say switch port access VLAN 20. And we can verify that these ports truly are members of these VLANs by doing another show VLAN command. And you'll notice for the lobby VLAN, we have gigabit 0/4 assigned to that VLAN, and for the employee VLAN, we have gigabit 0/5 assigned there. Now let's go over and do something very similar on DSW2. Let's go into interface gigabit 0/4 and also say that this interface belongs to VLAN 10, the lobby VLAN, and we will also say that interface gigabit 0/5 belongs to VLAN 20, the employee VLAN. Let's verify that with a final show VLAN command. And we see that these interfaces do belong to the VLANs that we configured. At this point, let's review what we have done. We began this lab, BCMSN lab number 1, by taking a look at how we could interconnect a couple of Catalyst switches with not just one physical connection, but with more than one physical connection. And the maximum number of physical connections that we can use, by the way, to interconnect these switches varies based on our switch platform. We just used a couple of physical connections between a couple of Catalyst 3550 switches to form an ether channel, logically bonding together the bandwidth for both of those physical interfaces into this virtual ether channel interface. Once we had configured and verified our ether channel, we then formed an IEEE 802.1q trunk across the ether channel, and a trunk allows us to carry traffic for multiple VLANs. And when we created our VLANs, instead of having to create the VLANs on each switch in our topology, we leveraged Cisco's VTP, the VLAN Trunk Protocol. VTP allows us to create a VLAN on one switch and have that VLAN database change propagated to neighboring switches. So we created a couple of VLANs on switch DSW2, and those VLANs were automatically learned on switch DSW1. And as a final step, we then assigned ports on our switches to belong to specific VLANs. We had broadcast domain isolation between the lobby VLAN and the employee VLAN.